Hello friend, this is Mike Ascuti again, and in this video I'd like to focus on two-dimensional nanostructures. These are basically very thin layers that are atomically thick in one dimension, and usually, at least in the first set of nanostructures we'll look at, they're surfaces. And so I'd like to begin by talking about the need for atomically thin layers, then talk about a technique that can produce them, atomic layer deposition, and I'd like to spend most of our time on self-assembled monolayers, which are the subject of this video. And then in the next video I'll talk about graphene. All right, now I will use a PowerPoint set of slides, but please take notes and write down the key points in your own notes. Why do we need atomic layer precision? Well, quite simply because the structures that we want to make in nanoelectronics, in nanoscale heat transfer devices, in nanophotonics, and even in nanosensors of all kinds and beyond, all of these require the control of layers that are on the scale of atoms. So for example, there's a picture here in this on the screen in the slide that I prepared of a transistor, and these are the kinds of transistors that we can purchase even right now. So here we have a source, a drain, and then a gate, and of course the gate controls how much current passes between the source and the drain. And if we look really close here, there's I'm going to cover it up with my single line here. There's a very thin layer right there of a few atoms thick, which is an oxide, and basically something that does not conduct electricity or charges. And that separates the gate from the channel. And this oxide is just a few nanometers thick, which means it's just a few, perhaps tens or hundreds of atoms thick. And this is only one example of many that can be found in nanotechnology. Now let me talk about one approach that you might think about if you were smart and you were tasked to create atomically thin layers, and this might be the way that you'd think of from a top-down approach. This is called atomic layer deposition. Now this provides the atomic level precision that we want in a deposition setting where we have a substrate and we want to add something to it. And it relies on what's called self-terminating surface reactions. And we're not going to get into the details of the chemistry here. And before I forget, I should call this ALD. All right, but this relies on self-terminating surface reactions, and the deposition proceeds one layer at a time. So that's the key parts of this, where we have a substrate and then we have some kind of molecule. And we don't even have to get into what molecule it is. But we expose the substrate to this particular molecule, and there's a nice reaction that promotes a chemical bond between one part of the molecule and the substrate, as I've drawn here. And then after purging the chamber, this gassy part, out, then we can wind up being left with just one layer. That's a monolayer, a single layer of a molecule thick on top of that substrate. And then in the next step, another material can be floated in, potentially a different reactant, and that can react with one or more of the atoms that were in that first layer. And then we can purge again, and then we wind up with something else, right? So we see that there's a dark blue atomic layer that's on top there. And then, of course, we can go through and do that again, and again, and again, and again. And using that technique, we can layer these structures one atomic layer at a time. But that's not the only way, and really in nanotechnology, there's this alternative way to look at things, which involves self-assembly. And so this new class, or this new topic that I'd like to introduce, is called a set of self-assembled monolayers. And for short, we call them SAMs. All right, so these are monolayers that are formed because of a self-assembly process that happens when molecules interact with each other. All right, but let's define some terms here. First of all, what is a monolayer? Well, a monolayer is a single two-dimensional layer of molecules. And this is often on the scale of tens of nanometers, so for example, 0.05, all the way up to a couple nanometers thick. And this occurs based on this principle. First, there's an adsorption of a single layer of molecules from a solution onto the surface. So this adsorption simply means that the molecules are connected to the surface somehow. And I'll show you some pictures in just a second. But here's the concept. There's an adsorption of a single layer of molecules from a solution onto a surface. And how is this done? Well, first, a solution is left to surround a substrate, or a substrate is left in the solution. Then, just as a matter of time, the molecules are chemisorbed onto the surface. In other words, they form strong bonds. And so here we have an example of the actual solution, and inside here would be a substrate of some kind. And then spontaneously, the molecules that are in this solution, if they're chosen just right, would chemically react and to bond onto this surface. All right, so now I'd like to unpack this a little more. But before I do, I want to just remind you of a distinction of our language here. And that is that there's a difference between something that is chemisorbed versus physisorbed. And we're not going to use these terms too much, but the literature does, and I'd like you to be aware of this. So first of all, there's this concept of chemisorption. And this quite simply is a process where a molecule from a solution chemically bonds with a covalent or an ionic bond. And because it's a covalent or ionic bond, it is a strong bond. In other words, it's a very high energy bond to break. And not surprisingly, it has a low reversibility. Right? So it requires either very strong etchants or perhaps a high temperature to remove it. Now, conversely, there's another way that the molecules can attach to a surface, and that is a physisorption. And in this case, there is an attachment that has to do more with van der Waals forces. And as we recall from the last set of videos, these are relatively weak, and so these can be broken relatively easily, and so they can be reversed fairly easily in room temperature. All right. The key thing to take away from this is that self-assembled monolayers, SAMs, can be designed for either of these. And so as a class of materials, they can do both. They can either be very strongly bonded or they can be kind of weakly bonded. So what is a SAM? Well, this is a good picture, and I would like you to write this in your notes very, very directly. The first thing to begin with is the fact that we start with a substrate. And on that substrate, then, are a bunch of molecules. And each of these molecules is a component of this SAM. And it's got three groups that I'd like to begin to point you to. First of all, there's the head. And that's the part that bonds to the surface somehow. And so that's the head group. And quite often this substrate is a metal, by the way. And so these would be atoms that like to bond, usually with metals. Then there's a backbone, and of course that's this part here, and that's usually very long, as is drawn here, compared to the width of the molecule itself. And then at the end, there's a tail. And at this point, this doesn't look like much of a tail, but this is a terminal group or a tail. And it is, of course, on the bottom side that we have the substrate, and then it's out here we have the rest of the world, or the outside world, which, to be honest, is usually some kind of fluid or gas, or perhaps another set of molecules that are going to be deposited on top of this. All right, so molecules and particles assemble on their own, and that's the magic of this self-assembly. They assemble on their own in this kind of forest because it's the lowest energy state for them. And they form a coating, and this coating is typically less than a micron thick, and sometimes the layer is just a single layer thick, and that would be called a monolayer. All right, so let's dive into this a little bit more. I'll show you some molecules. You don't have to worry. Don't be scared. We'll get through it. Now, there's a set of molecules that are constructed in such a way that they have a polar group on one side, meaning that they are attracted to water on one side of the molecule, and they're called hydrophilic. And this is an important word that you need to remember if you haven't encountered it too much before. So it's hydrophilic, meaning it likes water. And then on the other side of the molecule, there are chemical structures that repel water or are phobic to water, or the term is hydrophobic. And this kind of molecule is tremendously important in not only nanotechnology, but in our bodies and in biological processes. All right, and so this is called an amphiphile molecule or an amphipathic molecule. These are fancy names for the same thing. All right. What is an example of that? Well, a very simple example would actually be a few hydrocarbons with an oxygen and an OH group. And this is going to be the polar side of the molecule that's going to like water. And I hope you can see why H2O would be very comfortable with this. And then on the other side, you can see that there's a balance of charge. And so it's not going to be a polar end of the molecule. So that's one very simple example. A more complex example, but don't be too scared, is this one. And that is, we can see as a cartoon right over here, where we have a head group over here that's a sulfur terminating onto a substrate, for example, gold, and then a spacer, which is also much longer than it is wide, and then a tail. And I can see in this, illustration that I've prepared, or that this is called the head group. Now, what the head is and what the tail is can vary depending on who's talking about it. So don't be too troubled by that. But in general, in our textbook and in this class, we're going to use this illustration, which comes from your textbook. And that is that the head group attaches to the substrate and the tail, or the terminal group, sticks away from the substrate. All right, so in this example, the sulfur attaches to gold very strongly with a strong covalent bond, and then there's this flexible chain, and you should remember this is very, very flexible and wiggly, and then there's a head group on the top in this particular molecule. Now, what does this look like when it's actually forming, right? So we talked about putting a substrate in a solution, which of course will have a random set of these molecules. Well, if you look at just one portion of the substrate and imagine the initial time right after the substrate's put in, well, there would be a very first molecule that would come, and the part of the molecule, the polar part, or most likely the polar part, would bond very strongly with the substrate. And then from there, there's two paths that could happen when more of this molecule's friends come along. Now, they could come in a very dense way, and then what you, I hope, can see is that eventually the heads of those groups would be the only things that could attach to the surface if the density was enough. And then eventually, if enough of them connect to the surface, then the tails are going to stand up. And then it's going to wind up being a very nice, strong forest of these molecules. But the other path is, of course, where there's a low density initially, and then the tails actually lay down. And then the molecules, as they come in, eventually the tails repel each other, and then they start to stick up, and then we still get that same structure. So if we did some molecular animations and simulations, we would see something like this, where we wind up with a substrate bonding to each individual molecule, something like this, and then as new ones come in, they minimize the energy, they react, and then they lie down with their neighbors in just the right way. And quite often, it's the van der Waals forces between the molecules that result in this columnar surface, regardless of what the bond is to the surface. All right, now here's another very important example in nanotechnology, and this is a transistor where there's a source again, a drain, and a gate. And similar to the last transistor that we showed before, there needs to be an insulator between the channel, which really is this, where charge goes back and forth between the source and the drain, and the gate. And the gate controls how much current is going between these. Now, in this example, the SAM, or the self-assembled monolayer, is this molecule. So it has a silicon with 3 chlorine atoms on this side, and a very long hydrocarbon chain. And this nomenclature means that there's 15 carbon atoms here between the head and the tail. And then at the tail, there's this benzene ring that's connected through an oxygen here. And so that's this molecule here. I hope you can see it if you look very carefully. All right, and when this bonds to the surface, there's a whole bunch of these that can form a well-ordered, although not a crystal, but a well-ordered monolayer on top of something like silicon. And then on top of that can be put organic electronic layers. So a molecule, for example, pentacene, which is a organic semiconductor, can be deposited on top using other methods. And then finally, a drain and a source can be applied. And so just check out this whole process. This is all built on this self-assembled monolayer, which is a couple nanometers thick. It all depends on this self-assembled monolayer to be constructed. All right, one last variation on this self-assembled monolayer are molecules that will react and form with themselves, not so much on a surface, but with themselves. And I hope as a cartoon you can remember this molecule that we've seen before. This is again from your textbook, and it has a polar head and a hydrocarbon tail. And so if we put this in water with a whole bunch of its friends, well, what's going to happen? Well, as I hope you can expect, the polar groups of those molecules are going to be attracted to one another, and the tails are going to be attracted to each other. And so that's going to mean that they're going to spontaneously self-assemble into several structures, and these are just a few. The term micelle is the term that we're going to use for these kinds of spheres or balls, or perhaps you can think of them as molecular droplets, because the water is either going to be on the inside of this micelle or it's going to be on the outside. And I hope you can see that, again, if you have a whole bunch of parts of the molecules that like water, they're going to be on the outside. Right? So these are the parts that like water, they're going to stick out. And then those parts that do not like water, they're going to wind up in the inside. Also, it's possible, depending on how much water there is, to have the inverse. And this is an inverse micelle, where the water droplet is on the inside, and then those polar groups are all sticking toward the water. And then lastly, and this is the really interesting thing, is it's possible to have a bilayer micelle. And notice here what's happened. We have a bunch of polar groups on one layer, and then the nonpolar, or the hydrocarbon tails, the hydrophobic parts, sticking toward their neighbors. And then on the other end, there's some more polar groups. And this turns out to be a bilayer of these self-assembling monolayers. And in this case, it's forming a sheet, as is illustrated here, and that's called a micelle. Now, the most important example of this is the lining of our cells. And I'll post a video or point you to a video in just after this that will show you a very nice example of this. And what I want you to understand throughout all of this micelle kind of discussion is that these are not crystal fixed molecules, but rather they dance around because they're self-assembling and they always influence one another. So they're not covalently bonded to each other at all. It's just the van der Waals forces that are interacting between them. So not only are these kinds of micelles in our bodies, but also they're used in medical applications for medicine. So for example, micelles can make otherwise insoluble molecules of vitamins soluble by incorporating them into their dry core, for example, in here. But that's just one example. That's it for now.